In this installment, we are going to look at reading voltage levels through the ADC port of an array-based system. The RE6M4 comes with two ADC units, and each unit comes with multiple 12-bit channels with a sample rate of 5 million samples per second. To demonstrate the analog to digital conversion feature on array boards, we are going to take the example of a simple LED circuit powered by two AA-sized 1.5-volt batteries. In this circuit, there will be one voltage drop after the resistor and the rest after the LED. So, we can measure voltage at 2 points, that is the current battery level and the voltage drop across the resistor. So, as usual, we start by creating an array C++ project. On the device selection menu, we shall choose the board EK-RE6M4. We let the rest of the configurations remain at their default choice. For project template, we will choose the bare metal minimal option. Once we click Finish, the project files will be initialized. Once the project template is ready, we shall check the configuration of the ADC pins in the Pins tab. Under the Peripherals menu, the Analog ADC section contains the pin configuration for the two ADC ports available. The two channels have been assigned to P000 and P001, so we should unassign the channels not being used to prevent any noise. When we navigate to the individual pins configuration, we can see that these pins have already been configured for analog mode. Next, we will configure the stack for an ADC module. Under the analog menu, the R_ADC stack is available. The name has been set as G_ADC0 and we will let it remain as that. The resolution may remain at 12-bit. The other settings may also remain in their default state. Next, in the input properties, we need to check scan mask for channel 0 and channel 1. The reference voltage setting has already been set. For the next setting, we shall name a callback function for the interrupt from an ADC operation. We will double check the mode as single scan. Going back to interrupts, as we are using a callback function, we will need to specify its interrupt priority. We will also check if the pins have been associated with this stack. Now the configurations are completed. We can generate the project contents. Now we can start coding our application. We will open the hullentry.c file to write our code. First, we shall declare a flag variable for the ADC operation and set its value to false. Then, we will initialize a global status variable and two integer variables for storing ADC read values. We will also initialize two float variables to store the actual voltage values in volt unit. Then, we will define the ADC callback function. We can get the template for this from the Developers Assistance menu. As we are not using any pointer arguments here, we can put the FSP parameter not used macro. This macro is used to suppress compiler messages when a parameter is not being used in a function. Next, we shall call the ADC read function for both the channels. We will use the assert macro after each call to ensure the functions have been executed without an error. The ADC read functions require the arguments defining the ADC channel to be used and the variable to store the read values. So, we key in the name of the channels and the appropriate variables that we have previously initialized. At the end of this implementation, we shall set the ADC flag to true. Moving on to the hull entry function, we need to call two functions for the ADC operation. First, we need to open the ADC channel. Second, we need to initialize the scan configuration. Then, we can create a while loop and execute the ADC scan function. All function API related to the ADC operation is taken from the developer's assistance menu. Once we have executed the scan, we shall access the ADC values using the ADC read function. However, we can only read the values when the scan has been completed. Therefore, we have written the ADC read function as part of the callback function. So, when the callback function is executed and the flag value is set, we can perform some additional operations to process the ADC values. We will process the raw data from the ADC, which is an integer between 0 and 4095, since the ADC is a 12-bit unit, where 4095 would correspond to a voltage level of 3.3 volt based on the operating voltage of the RA6 M4. Once we have made the calculation and stored the values, we shall add a software delay. Our coding is completed and we can now build the project. Reviewing the circuit we are using for this demonstration, the ADC values are obtained from 2 points in the circuit, with channel 0 showing the live voltage level of the battery and channel 1 showing the voltage drop across the resistor. We would also need to connect the negative terminal of the battery pack with the ground pin of the EK board to align the ground voltage levels. Once the circuit connections are done, we can debug the project and upload to our board. In the debug perspective, we can utilize the expressions function to monitor the ADC values in real time. We first need to key in the name of the variables we are interested to monitor, and then we need to run the program. As the program is running, we can monitor the real-time values stored in these variables. And that concludes our demonstration of the ADC operation on an EK board for RA microcontrollers.